Okay, so here's a really fascinating engineering mystery for you. You design this beautiful, perfectly parallel, just neatly organized ribbon cable to route signals from one board to another. It looks incredibly clean, right? Yet, the very second you run high-frequency data through it, it unexpectedly acts like this massive antenna, picking up magnetic fields, radiating noise everywhere, and completely ruining your system's EMC compliance. So, why do these visually clean cables create such incredibly dirty signals? Well, the answer doesn't actually lie in the wires themselves, but in the invisible geometry of the currents flowing through them.
Here's our roadmap for today. 1. The ribbon cable dilemma. 2. Fixing the loop area. 3. Shielded ribbon pitfalls. 4. The long cable illusion. And finally, 5. The golden rules of cabling.
All right, kicking things off with part 1, the ribbon cable dilemma.
Think about a standard wiring harness compared to a ribbon cable. A standard random wiring harness is essentially like a chaotic city intersection. The position and orientation of the wires are random, and they vary from one unit to the next. Because that geometry is so chaotic, the noise performance is entirely unpredictable. A ribbon cable, on the other hand, is what we call a controlled cable. Think of it more like a structured multi-lane highway. The geometry is completely fixed. Now, this is fantastic for low-cost, predictable routing. But because these signal lanes are locked in right next to each other, this highway is highly prone to massive crosstalk if we don't strictly manage the traffic. And by traffic, I mean our signal and ground assignments.
Let's look right here at configuration A. Notice how we have just one conductor acting as a ground, and all the remaining conductors are signal leads. Sure, this minimizes your overall wire count, but it is an absolute disaster for EMC. Why? It comes down to the physics of magnetic field coupling. Let's look at the foundational equation from our source text, the induced noise voltage. V sub n equals J times omega times B times A times cosine theta. Let's break down what that math is actually telling us. Omega is our frequency, B is the magnetic field density, and A is the loop area. When multiple signals share just one distant ground, the return current has to travel all the way across the width of the ribbon. Physically, this creates a massive loop area, the A in our equation. It's literally like dragging a giant wide net through the air. That massive net catches all the surrounding magnetic flux, creating severe common impedance coupling and radiating noise everywhere.
Let's move on to part 2, fixing the loop area. Take a look at configuration B. See what we did here? We inserted a ground conductor right next to every single signal conductor. By doing this, we give the return current an immediate, adjacent path straight back to the source. Going back to our equation, we've just shrunk that loop area, variable A, down to almost nothing. We basically folded our giant net into a tiny, tightly controlled line. This drastically reduces the magnetic field pickup, totally kills the antenna effect, and isolates our signals. Now, yes, it requires twice as many wires, but it is the preferred and honestly often strictly necessary configuration for a ribbon cable.
Now, check out configuration D. This is an advanced tactic, a ribbon cable with a full-width ground plane running underneath the signal wires. Let's put some real concrete numbers to our loop area equation. Remember, V sub n equals J times omega times B times A times cosine theta. Imagine configuration A gave us a wide loop area, our A, of 2 square inches, which was inducing, say, 100 millivolts of noise. By moving to configuration D and placing the signal over a full-width ground plane, that loop area shrinks to just the microscopic gap between the wire and the plane directly beneath it. So we might shrink A from 2 square inches all the way down to 0.02 square inches. Because noise voltage is linearly proportional to area A, our 100 millivolts of noise drops 100-fold, right down to 1 millivolt. The math is absolute. But, and this is a massive but, here is the critical engineering condition. The connector must make a full-width, continuous electrical contact to that ground plane. If your connector only grounds at a single tiny point, the high-frequency return current is violently forced outward to find that pin. This destroys your carefully planned geometry and instantly blows up your loop area all over again.
All right, part 3, shielded ribbon pitfalls.
Now, I want to prepare you for a very specific, non-intuitive trap. Look at this quote based on Palmgren's research. In a shielded ribbon cable, the outside conductors are typically 7 decibels less shielded than the conductors in the center. Why does that happen? Well, it's because the shield current is simply not uniform at the absolute outside edges of the cable. The physical geometry causes the shield current to behave differently at the margins, which literally leaks noise. So the practical takeaway here is absolute. Never ever place your critical, high-frequency signals, like your system clocks, on the outermost wires of a shielded ribbon cable.
Keep those critical signals safely tucked in the center lanes.
Moving right along to part 4, the long cable illusion.
Okay, we need to throw a bit of a wrench into the standard low-frequency model. Let's define what makes a cable electrically long. A cable becomes electrically long when its physical length approaches 1/4 of the signal's wavelength, written as lambda over 4. Now, at low frequencies, a signal wavelength might be miles long, right? So the current on a typical cable is all in phase. But at high frequencies, that wavelength shrinks drastically. When the signal moves so fast that 1/4 of its wave actually fits onto your cable, the wave crests and troughs exist simultaneously on the exact same physical wire. The currents are literally shifting out of phase with one another along the length of that cable.
Take a really close look at this graph. Notice that dashed, straight line? That represents the short cable approximation. In low-frequency theory, we falsely assume that as frequency goes up, noise coupling just rises and rises indefinitely forever. But look at the solid black line. That's the transmission line model. In reality, once the frequency hits a certain point, the noise voltage completely stops climbing linearly and begins to oscillate, creating standing waves. You see, the universe doesn't actually allow infinite noise coupling. High-frequency physics steps in and alters the entire behavior.
Let's walk through exactly when these thresholds happen step by step. Step 1, up to 1/10 of a wavelength, lambda over 10, the standard low-frequency approximation is exact. Step 2, up to 1/4 wavelength, lambda over 4, the approximation is still useful, though it is definitely beginning to deviate. Step 3, beyond lambda over 4, phasing effects completely dominate the situation. In fact, when the cable reaches exactly 1/2 wavelength, lambda over 2, the out-of-phase currents actually cancel each other out. This drops the external coupling effectively to 0 at that specific frequency. The physical parameters determining the coupling haven't changed at all, but the numerical result is governed entirely by wave phasing.
Finally, part 5, the golden rules of cabling.
All right, here is your rapid-fire recap. These are the 3 golden engineering rules you absolutely must memorize if you want to ensure signal integrity and pass EMC testing. Number 1, decrease your pickup loop area. This is the absolute key to stopping magnetic field coupling. Number 2, always terminate your cable shields to the metallic equipment enclosure, never to your internal digital circuit ground. If you terminate to circuit ground, you are just injecting shield noise right into your logic. Number 3, strictly manage your ribbon cable assignments. You really want to aim for a 1-to-1 signal-to-ground ratio and never, ever exceed a 3-to-1 ratio if you want to survive ESD and transient coupling.
To wrap things up, I want to leave you with a bit of a provocative thought. We just proved mathematically that spreading a signal and its return ground far apart in a ribbon cable creates a giant loop area that acts just like an antenna. So go look at your printed circuit board layouts. When you route a high-speed trace directly over a split or a slot in your PCB ground plane, you're forcing that return current to take a massive detour around the gap. So what do you think that slotted ground plane is actually doing? It's doing the exact same thing. It is creating an antenna. Master the loop area and you will master EMC. If you found this technical breakdown valuable, make sure you hit subscribe for more rigorous, mathematically grounded automotive and EMC survival guides. Thanks for joining me on this explainer.